Let's get started. Today we'll talk about recursion a little bit more, and we'll do the test review for your test on Tuesday. Currently, right now, I believe homework 6 is due Saturday night, maybe Sunday night. If you need an extension, request it as usual using the WebAssign. So what we need to do is talk about recursion just a little bit more. You have a few problems on homework 6 that you need to prove by induction. I'm going to work one of them. So we'll do that, and then we'll get into recursion. So one of the parts of problem 1 you have to do So here's the problem. We want to prove this is true by induction. So what is this on the right-hand side? What do we call it? We don't call it polka dots. You have no ideas. Closed form. We call it closed form because I don't have to have any dots in it. What's on the left-hand side? Yeah, it would be nice if it was called open form. But this is a summation. And it's always also called a series. So a lot of times we want to prove that these two things are equal, so I can use a closed form or a formula instead of doing a series. Why would I want to use this instead of that? It's shorter, a lot less calculations. Also, how many calculations are over here? And of them, how many calculations are over here? 1. So, can you think of a time where I might want to do this one instead of that one? No? When n is small? Maybe? And I might have to do it by hand, maybe? So you might want to do this one if I have to calculate all these numbers anyway. Right? Because I actually could write this recursively. Because the sum on the left-hand side, let's say that this was called f of n. And I could write this as a recursion as f of n minus 1 plus what? Well, if you can't answer that question immediately, you should figure out what f of n minus 1 is. So I want you to write that on your paper. What is f of n minus 1? What goes in the blank? N minus 1 times n minus 1 factorial. That should not be hard. That is one of the reasons why you take this class, is to practice doing things like that, is to recognize if I change an input, how does that change what I'm actually calculating. So now that you know what this is, what's the difference between these two? So if you don't know what this is, I can subtract them. So what do I get if I subtract the left-hand side of f of n and f of n minus 1? So over here, I just get f of n minus 1, right? What do I get on the right-hand side? I just get n times n factorial, right? Because all these other terms line up. Everything else here is in f of n. Yes? All the terms in f of n minus 1 are actually in f of n. So the only difference is this last term on f of n, so I can just write this. So there was a question on the piazza about what is the cheat method for finding a recurrence. So here is a function, and the cheat method for finding a recurrence is by writing a definition of that function for an earlier number and then subtracting them. So the definition of a recurrence is something that uses a smaller value as an input for the function, so the function actually refers to an earlier value. So that's the definition of a recursion. So you have to have something that looks like this. Doesn't matter what that is, and then some other stuff. So a recurrence looks like that, and it has to have one other thing. And what is that? It has to have a basis, right? Because I can't look back forever. I have to start somewhere. So in order to make a basis for this, what would make sense to start at? Should I start at f of 0? No, because I don't have any zeros in my formula. It would make more sense to start at 1, right? So I write down what f of 1 is, and it's equal to 1 times 1 factorial, which is equal to 1, right? So now we have a recursive definition for this. And we have a closed form also. So there's a few different things here that we could prove are equal. I did just want to show you the cheat method. So that's what that is. So the cheat method is if I need to come up with a recurrence for something, so if I have f of n equals something, I figure out what f of n minus 1 is. And that's not hard to do because all I have to do is copy everything, and everywhere I see an n, what do? I replace it with n minus 1 and put parentheses around it so I make sure I don't make any errors. And then I just need to subtract one from the other, and then whatever I get over here is, let's say that's a and this is b. I get a minus b, and then I just solve for f of n by adding f of n minus 1 to both sides. And then I figure out what the basis is. So whatever it happens to be, I just write that down, and now I have a recursive form. So if I've ever given you a formula that's a closed form and I ask for a recursive form, that's all you need to do. Now, on the example we looked at the beginning, anything that is a nice sum like that is really easy to write in a recursive form. Because there's n terms, and so the nth one is very easily written in terms of the n minus 1 one because it just has one more term added on to the n. So that should be easy. That process is something that we do both for making a recurrence and for making a summation, figuring out what formula goes in the middle of the summation. So that's what I want to do next, is figure out how do I write the summation for this. Can I do what? Show the bottom? Yeah. So I'll do a couple of examples of this in a minute. So we're going to do a summation for this and a proof, and then we'll go back to the cheat method. So right now, while people are writing this down, if you already have it written down, go ahead and figure out how you write the summation for the left-hand side of f of n here. Okay, so the process I go through is I write down the summation, and then I try to figure out what the last term is, and I write it instead of with n, I write it with k's. I like to use k's instead of i's because i's look like 1's, which also look like l's. So that's why I use k's. So that's what I recommend to you so you don't get mixed up about which thing is which and make a mistake. Okay, and then I have to have a k equal something on here. Yes? This is k times k factorial. So k factorial is a function, and it gets multiplied by k. So if the factorial was applied to k times k, there would be parentheses around k times k. Thank you for the question. Okay, so now I need to figure out where k starts. What's the smallest term in the summation? 1, so k should be 1. And then the largest is n. So that looks pretty good. And then I can copy over the right-hand side. All right, so let's prove this by induction. So I'm going to write the left-hand side. Now, you might be tempted to write 1 times 1 factorial inside that summation, but you shouldn't, because all I can do is replace the n's with 1's. So this is 1 times 1 factorial. 1 factorial is just 1, so that's 1. And this is 2 factorial minus 1. 2 factorial is equal to what? 2, because it's 2 times 1. So we get 2 minus 1, which is equal to 1, and that is equal. Then I write assume, and I copy over what I'm trying to prove. And then I write the prove, which is exactly the same, but everywhere I have an n, I replace it with n plus 1. Notice that I don't change what's inside this summation because there's no n's in there. So there's my problem set up. And then we start with the left-hand side of the prove. And set it equal to the left-hand side of the assume. And then I have to fix it. And we just figured out that the difference between these two was just the last term, which is n times n factorial. And then I can replace the left-hand side of the assume with the right-hand side of the assume. So you still leave this here. So the right-hand side of the assume says that that's n plus 1 factorial minus 1. So that's the right-hand side of the assume. So I'm just doing a substitution. And add n times n factorial. Because that's what's over here. Yes? Yes, thank you for fixing that. Sorry about that. I'm going to write that over again. By the way, you can do an assume with n minus 1 and prove for n, so that is fine. You can choose whichever one you want to do. Okay, so I replaced that with n plus 1 factorial minus 1, and then just copy down the rest. All right, now what we need to do is get it to look like n plus 2 factorial minus 1. So I've got the minus 1, right? I just need to combine the other stuff so it can make it into an n plus 2 factorial. So the first thing I need to do is just get them together. So I'm going to put the minus 1 on the right-hand side. Does anybody have an idea of what to do next? Factor out an n plus 1 factorial because it's in both of the terms. And what I get after I factored out here is a 1. So I get 1 plus the quantity n plus 1. And then I still have the minus 1. So I factored out an n plus 1 factorial out of the first two terms. And inside the parentheses, we have what? N plus 2. And so is there any magic you can do to finish this problem? That is the definition of n plus 2 factorial, right? This right here is the definition of n plus 2 factorial. Raise your hand if you see that. Raise your hand if you don't see that still. Okay, so n plus 2 factorial is the product of all the numbers from 1 up to n plus 2. N plus 1 factorial is the product of all the numbers from 1 up to n plus 1. So the only difference between those is to take n plus 1 factorial and multiply it by the missing term, which is n plus 2. And if that doesn't make sense, you should write it out on your paper. So now we're done because we have the right-hand side looking like what we wanted to prove. And all of these are fully reversible things that we've been doing, so everything on each line is equal to the last line. Any questions on this problem? Yes? No, I don't. No. You don't need to copy down the left-hand side of the proof if you've already got it on the paper. So, you know, when I start doing my equals, as long as I've got it there, it's fine. Yes?
When you started out doing this problem,
yes.
you were doing a bunch of recursion stuff,
yeah.
and then you switched over to doing an induction proof. Are those usually going to be tied together? Or?
No, I was just pointing out that we could write a recursion for it because that's something else I wanted to do today. So we're going to go back to that now. So this is a separate problem. I'm sorry that was confusing. So separately, we figured out how to write a recurrence for the left-hand side of this, and then we did an induction proof that the left-hand side is equal to a closed form. Thank you for asking that question.